Okay, now I want to describe what does it mean to say that a random variable x converges as n goes to infinity to a random variable omega x. Okay, xn converges to x. Okay. Now I remind you that if this were just a number, a sequence of numbers, then I remind you that say the limit of a sequence the limit that xn converges to x when n goes to infinity. This means that for any epsilon positive, you can find a large n such that for all n larger than n, the deviation of xn from x is less than epsilon. Okay, so so this means that your sequence is from a certain point onwards, it will be very close to the limit, as close as you like. Okay, so this also means that the number of n such that this deviation is larger than epsilon for any epsilon is finite. Okay? So because this n, so for any n I can find a finite n such that this is true. So this means that no matter what is epsilon, the number of terms in the sequence which are far more than epsilon from the limit is finite. Okay. Okay. So this is what happens with sequences. Now, what happens with random variables? Well, the problem is that random variables are functions, so they depend on omega. So we have to think about convergence of functions. And there are different ways in which you can define this convergence. So the first one is almost sure convergence. So what does almost sure convergence means? Well, it means that so if I fix omega, then for a fixed omega, then this limit is just a limit like this one. So and so it tells so essentially you for a fixed omega you can find an n that will depend on omega, such that from a certain point onwards, from this point onwards, all your sequence will be less than epsilon. But this n depends on omega. Okay, so what almost sure convergence means is that the probability that your omega satisfies, so that your sequence for a given omega converges to x in this sense is equal to 1. Okay, that almost surely this limit will occur. So you can specify this more precisely in the following way. So you can say that for any epsilon and delta positive, however small you define it, so there is an n that depends on epsilon and delta, such that the probability that the deviation from x is less than epsilon for all n larger than this n epsilon and delta, this is larger than 1 minus delta. Okay? So, you see, essentially, this is the same statement as this one, because it essentially tells you that with probability which is arbitrarily, which I can make arbitrarily small to 1, there will be an n beyond which these deviation do not occur. Okay, deviation larger than epsilon do not occur. So indeed, you can also say that the same thing can be said by the following way. So let's define this event an as the event that x of n deviates from x more than epsilon. Okay. So almost sure convergence, so that xn converges almost surely to x as n goes to infinity, is equivalent to saying that the probability that an occurs infinitely often is equal to 0. Now this is the same statement as here. Okay, so it's saying that the probability that the deviations larger than epsilon occur infinitely many times is equal to 0, which means that the probability that that the number of points for which this deviation occur must be finite, okay, with probability 1, which means almost surely, okay. So, by the way, say almost surely, so this, we will frequently use these terms, and you will always find it. So A dot S dot means almost surely, and IO means infinitely often. Okay, so so let me spend a couple more words on what does this event an occurs infinitely often means. So this means that essentially there is an infinite subsequence of values of n such that the event an occurs, and almost surely there is a there is one of these subsequences. Of course, the subsequence will depend on the particular realization omega, but the way in which you can write this is by saying that no matter how I fix n, if these events occur infinitely often, no matter how fix an m large, there will be for sure at least one event that occurs for n larger than n. Okay, this you can write it in the following way: that for any m, there is at least one n which is larger than m, for which the event an occurs. Okay. So notice that this is the equivalent of for any, and this is the equivalent of say that there exists at least one of the events larger than n. And so this statement here is exactly the statement that I was making here. So it tells you that if an occurs infinitely often, then it will occur at least once beyond any finite value of n that you can fix. Okay, so the other another way in which you can define the convergence is convergence in probability. So convergence in probability means you say that xn converges in probability to x as n goes to infinity. This means that the probability of having deviations larger than epsilon, the probability of an goes to 0 as n goes to infinity. Okay? So, well, an is this event. So you see that this is a weaker condition than this one, because it is only stating what is the probability that an occurs at a particular n, and how this probability behaves as n goes to infinity, whereas this condition is a condition that involves infinitely many events, deviations from the limit. Okay, so indeed, what you can show is that almost sure convergence implies convergence in probability. Okay, so this is another way in which you can define another definition of convergence, which is convergence in mean square. And you say that xn converges in mean square to x as n goes to infinity, if and only if, so this essentially implies that the expected value of xn minus x squared, the deviation squared, converges to 0 as n goes to infinity. Okay, and now convergence in mean square implies convergence in probability, and one way to show this is by the use of Chebyshev inequality, which is a simple result which is worth being remembered. So so the way to derive Chebyshev inequality is if you write the expected value of a random variable z squared, the square of a random variable, and so this is clearly the integral from minus infinity to infinity dz. These are real random variables, so of z squared times p of z. Now, say for any a positive, I can split this integral in the integral from minus a to a and from minus infinity to a and a to plus infinity. And of course, because this is all positive, so this will be larger or equal than just the integral when z is larger than a of dz times z squared p of z. And this is clear because this is, I just took one part of this integral, okay? But now in this integral, z itself, z squared, is larger than a squared. So I can say that this is larger or equal to the same thing where I substitute a squared to z squared. So this is a squared times the integral dz for z larger than a of p of z. And what is this? This is nothing but the probability that z is larger than a. This is a squared times the probability that z is larger than a. Okay. So if you take this around, then you get Chebyshev inequality, which tells you that for any real random variable z, the probability that z in absolute value is larger than a can be bounded above by the expected value of z squared divided by a squared. Okay, so this is what is called Chebyshev inequality. Okay. Now it is clear that if you use Chebyshev inequality with the variable z, which is xn minus x, then here you have you have that for any a positive or for any epsilon positive, so take a equal to epsilon, you have that the probability of an which is the probability that this thing is larger than epsilon, is less or equal by Chebyshev inequality to the expected value of xn minus x squared divided by epsilon squared. But if this goes to 0, as n goes to infinity, if this goes to 0, then also this goes to 0. So convergence in mean squared implies convergence in probability. Okay. Okay, the last notion of convergence that I want to discuss is instead convergence in distribution. And it's also the weakest form of convergence. So you say that a random variable xn converges in distribution with a random variable x as n goes to infinity if for any continuous function which is also bounded, for any bounded continuous function, the limit as n goes to infinity of the expected value of f of xn is equal to expected value of f of x. Okay, so so what does this mean? Well, this means essentially that if you take the difference between the expected value of this and the expected value of this is essentially the integral in dx of f of x times on one side you have the distribution of the PDF, is the PDF of x of n, and here you have the PDF of x. And so what convergence in distribution means is that this limit must be equal to 0 for any function f. So this essentially means that Pn of x should converge to P of x as n goes to infinity on all values of x but a set of measures 0. Okay, so this is why it's called convergence in distribution, because it tells it's essentially a statement that the PDF, the probability distribution of x of n, converges to the probability distribution of x.